Okay, so now let's look a little more into the concepts behind inverse functions, and we're going to start with what's called the reflexive property. Now, this is a pretty cool property that you're going to see that especially is helpful if you're good with geometry. And what it says is that if we have the graph of f with the point A and B, then this means that the f inverse has to contain the point BA. So we go from AB on the graph of f to BA on the graph of f inverse, which we kind of mentioned and in the previous part of this lesson, where the domain of f becomes the range of f inverse, and vice versa. The range of f inverse, or the range of f, becomes the domain of f inverse. So basically, you're just swapping the x and y coordinates. So a simple proof and how we can show this is by starting with the point AB being told that it's on the graph of f, which means that f of A is B, because remember, that's your x and B is your y. So we go from x to y. Then that means if we take the inverse function of B, that's the same as taking the inverse function of f of A. And we're told that f of A is B. So we're basically, swapping this and undoing we're undoing f with f inverse. So we're left with just A. And then that basically just means that if AB is on the point of f, then BA is on the graph of its inverse function. And we can basically show that for all of the points. And we can show the opposite of this if we have that f of b equals a. If AB is on the graph of inverse, we can basically use that same logic. I'm not going to go through it. I'm not going to go through all of that, because this is a simple logical proof by understanding this graph, which let's go into now. We call this a reflective property because if you were to graph f and f inverse, you're going to notice that the graph of f, when it's flipped over the line y equals x, is the same as its inverse graph. So you can figure out what the graph of f is, visually by by picturing what this line would look like if you reflected it over this line. So let's see if you can if you're good at geometry. So let's look at like an example of what I mean here. So we have XY plane. Let's say you have the graph of f. And the graph of f is this guy. This is what f looks like. So think for a minute. If this is the graph of f, if I was to reflect this graph of this graph of f across the line y equals x, so across this line, what would the graph of its inverse be? So think for a minute in your head if you can figure it out. And what you should be getting is that its inverse looks like that. So it's like bending this over that line. Let's add a little more to this. Let's see if we were to have this graph. Let's say we had let's say that f looked like this, and on this side it did this. So if we were to reflect this graph across the line y equals x, what would its inverse look like? Think for a second. I can try to mentally picture it if you can. What would this graph look like if you flipped it over that line y equals x? Now what you should get is that its inverse graph will look like this on this side, and on over here it's going to be doing this. And you probably remember or probably can recognize that this is basically like the cubic graph, the line x cubed, and this graph, or no, this is the cube graph. F inverse is the cube graph, and f is the cubic graph, or x to the 1/3 power. And just think about it, cubing and taking the third root undo each other. So they're inverse functions. So that, again, geometrically will make sense. Now, the next question is going to be like, well, when does an inverse function increase? Or no, when does an inverse function exist? How do we know when it exists? Now, there are two things that we need to recognize, two basic rules. So an inverse function will exist if the function is 1-to-1. Now, I want to talk about in a second what 1-to-1 means. The first thing is that we need to make sure that the function has an inverse function. How do we do that? We check to see if it's 1-to-1. But then how do we do that? How do we know if it's 1-to-1? Well, if f is what's called strictly monotonic, which means it's always increasing or always decreasing, then it's 1-to-1. So we want to check that f is strictly monotonic. So we want to check that f is always increasing or always decreasing. If that's true, that means it's 1-to-1, and that means it has an inverse. And the big deal here is that why this is important is because not every function has an inverse. That's something you want to make sure you understand. So let's kind of talk about or show an example of what this means and like why this is. So let's say we have this function. Let's take the cubic or the parabola function, for example. So the function y equals x, probably one of the first things you learn in algebra 2. This is an example of a function that's not 1-to-1. Why is that? It's because when something is 1-to-1, you want to basically think of it as having a unique y value for any x value, meaning that if you shouldn't be able to find any y values that are the same for two different x values. So on this graph, we have the point 1, 1, but we also have the point negative 1, 1. So we have two different x values that give you the same y value. So this is not 1-to-1. So think of it, there's only one way to get that any y value. There's only one way to get 1. There should be only one way to get 4. But to get 4, as you know, you can also have x is -2. So we can show there's a lot of values for this graph that's not, that's going to show it's not 1-to-1. Because again, you want every y value to only have one x value that you can get it from. So not 1-to-1. So when a function is 1-to-1, an example of a function that is 1-to-1 would be something like this. Let's say this is a square root function, so y equals the square root of x. This is 1-to-1 because there's only one way to get any y value. To get the y value of 1, there's only one x value that you will get it from, which is 1. To get the y value of 4, there's only one x value you can get it from, which is 2. And this is you can show it for every x, you can show that for every y value. There's only one x value that will give you any y value. So this is 1-to-1. So yes, 1-to-1. Now the second part is, the monotonic part. Why do we need to know if a function is monotonic, like always increasing or always decreasing? Why does that mean it's 1-to-1? Well, just think about it intuitively. Like, when a function is 1-to-1, that means you can never have a y value repeat. So if you start at any point here, let's just start at any point. Let me actually draw another graph here. For a function to be strictly monotonic, it's always increasing or always decreasing. So let's just start at 0, 0, let's say. Now, remember, I want it to be 1-to-1. So I'm going up, I'm going up, I'm going up, I'm going up, I'm going up. Now, if I at any point decided you go down, even for a little bit, that means like there's a y value that's the same for two x values. So even though this is a function of x, this wouldn't be 1-to-1 because again, you have 2 points at the same y value from two different x values, but you can just think logically, it's not always increasing because at some point to get back to that y value, it has to go to the opposite direction. It has to go down. So this would again not be 1-to-1, and it's not strictly monotonic. And you can basically do that same thing. Let's just call this f for another function. If a function is decreasing, and it does, at some point it increases even for a little bit, there's going to be y values, two y values at least that have the two y values that are the same for two x values. So it's decreasing up to here, then it increases and it goes back down. So this is not strictly monotonic, and it's not 1-to-1. So if you wanted something to be 1-to-1, you can never, once you start going up, you can never go down. You always have to be increasing. Like this one's always increasing. So f prime here is always positive. And here, this graph is always decreasing. It could be decreasing very slow or faster, but g prime, the derivative, is always negative. So that's just kind of the logic and rationale behind why a monotonic function is 1-to-1. Which again, if you really want to understand this stuff, really take time to absorb this and think about it, because then inverse functions become a lot less complicated. Okay, so let's go through now some guidelines on how we can find the inverse function for given a function, and then let's go through an example. So if we want to find an inverse function, first make sure if f is strictly monotonic, because if it's strictly monotonic, then it has an inverse function, then you can proceed. If it's not, then you just stop, because there's no point of trying to find it because there isn't one. It's not going to have an inverse function. Next, sometimes maybe in algebra 2, you probably learn like to swap x and y. Basically, you want to swap x and y, or think of it as solving for x in terms of y. This is more the formal way to look at it, but it's really like steps 2 and 3 are kind of basically the same thing. Now, once you get that value, once you solve for x as a function of y, then you basically are done. But let's make sure to define the domain of the inverse as the range of the regular function, and vice versa. And then if you wanted to furthermore make sure that you got the right thing, make sure that you got the right equation for the inverse, we can go back to what we learned at the beginning of this lesson, where we show that f of f inverse of x will give you x, and vice versa. If you take the inverse of f of x, you'll get x as well. Anyways, let's go through an example. So we want to find the inverse of f of x, where f of x is the square root of 2x minus 3. Okay, so we got to show that this is strictly monotonic. So we want to show that the derivative is always positive or always negative. So let's first find the derivative. So f of x, or f prime of x, remember this is the same thing as 2x minus 3 to the 1/2 power. So f prime of x will equal to 1/2 times 2x minus 3 to the negative 1/2 power, times the derivative of the inside, which is just the derivative of 2x minus 3, or times 2. These 2's cancel, and this becomes 1 over the square root of 2x minus 3. Now, so like, is this going to be defined for all x values? And is it always going to be positive, or is it always going to be negative? So let's recall, we can only take the square root of something that's 0 or more. So let's make the 2x minus 3 greater than or equal to 0. So going back to your pre-cal days. So then that means x has to be, after adding the 3, dividing by 2, x has to be at least 3/2. Now, if x is always at least 3/2, that means that this will always be positive, because the square root of any number, we can only take square roots of positive numbers or 0, but we're making it greater than, again, we're making it greater than this. So then we can show that if we have 1 over a positive number, this is always positive. This is always a positive number. So the derivative is always positive. So then if the derivative is always positive, that means it's always increasing. So that means it's strictly monotonic. So let's write that. So since f prime is greater than 0 on the interval 3/2, comma infinity, it is always increasing and strictly monotonic. Okay, so that's the first main part that we want to make sure that we do. The other part is, the next part is really just algebra, where we just solve for, we just solve an equation. So what we can essentially do is, remember, this is the same as y being equal to the square root of 2x minus 3. But if you replace, y with x and x with y, so if you swap them, so this is the equation that you want to solve this equation for y. So what you can do is you can square both sides. So you get x squared is 2y minus 3. And then add the 3. So we get x squared plus 3 equals 2y. And divide by 2. So then you get y being equal to x cubed plus 3 all over 2. So remember, the y is your output. In this case, our f inverse function is x cubed plus 3, not x cubed plus 3, x squared plus 3. X squared plus 3 over 2. All right, so there you go.